Good morning, everyone. Let's start with a quick public safety announcement. If while walking the halls of BITM today, you happen to encounter someone who looks just like you but is made up of antimatter, whatever you do, do not shake their hand. The resulting annihilation would release an enormous amount of energy, and frankly, it would quickly ruin our premises.
So, welcome students, teachers, and science enthusiasts to the Birla Industrial and Technological Museum. Today is a very special day. We are gathered here to celebrate our 68th Foundation Day. For nearly 7 decades, this institution has been sparking curiosity, and looking at the energy in this room, I'd say the chain reaction is still going strong. Today's lecture is going to take us deep into the weird, wonderful, and slightly chaotic subatomic world. The topic, particles and antiparticles. By now, most of you are well acquainted with protons, neutrons, electrons. But what happens when the universe decides that every particle needs an alter ego? Why did the brilliant physicist Paul Dirac even dream up the concept of antimatter using just pure mathematics? How was the first antiparticle, the positron, caught red-handed? And what on earth is the strange and unsettled ongoing drama surrounding the neutrino? To guide us in this quantum mystery, we couldn't have asked for a better co-pilot. We are honored to host Professor Palash Baran Pal. May I please request one of our colleagues to please come up and help us felicitate him. May we have a round of applause for him, please? Professor Pal is a theoretical physicist who retired from the Saha Institute of Nuclear Physics in 2017. If any of you decide to pursue high energy physics in the future, you will inevitably study from his textbooks. His research, particularly his seminal work on neutrino physics and the relativistic treatment of particles, has raked up over 6,700 citations worldwide. But what makes Professor Pal truly special is that he doesn't just speak the language of complex mathematics. He's a passionate champion of popularizing science in Bengali. He has literally bridged the gap between physics and linguistics, developing digital tools to ensure precise scientific writing in the Bengali script. And every stable atom needs a solid nucleus to keep everything from flying apart, and BITM is no different. Please welcome, with a big round of applause, the nucleus of today's event, Director, Birla Industrial and Technological Museum, Shri Arnab Chatterjee, to officially play host to this session and deliver the welcome address. Over to you, sir.
Today's distinguished speaker, Professor Pal, respected teachers present here today, my dear students and colleagues. On the outset, a very warm welcome to BITM Kolkata and a very good morning. As is just pointed out by Aditi a few moments back, we are celebrating the 68th Foundation Day of this organization, of this institution. And like previous years, this year also, we have chosen this very topic of matter and antimatter. There are two very reasons we have selected this topic. The first thing is that the very last Nobel Prize, if you remember, was on the theme of from lab to life. So here also, we are going to discuss one subject which was even a decade back was a part of some science fiction pages, and even people could hardly imagine that someday such topics will be dealt with in a lab. So here today we are going to discuss one such matter which is no longer a part of only science fictions, it's a reality. Secondly, whatever we study, whatever we learn, the wisdom, the purpose gets fulfilled only once we apply it, and apply it for the benefit of humankind. And today's subject, it is one such subject which is actively used in medical science. Many of you might have heard about the PET scan. The PET scan is used for detection of cancer cells. And it is called positron emission tomography. So the same way, here also the purpose is it can only get fulfilled if and only if the knowledge, the wisdom is applied for the benefit of the humankind. So with this brief introduction, I won't like to stay in between you and the speaker for long. I hope you all are eagerly waiting for the talk. So I'll stop here and wish you a pleasant stay and an enriching talk ahead. Thank you.
Thank you, sir, for those inspiring words to kick off our 68th year. So students, please prepare to have your minds expanded and delve into the mirror universe of antimatter while we set up the stage for the lecture.
I thank the organizers for inviting me in this nice occasion. And also because of this, I learned that the Birla Museum is just a little bit younger than me. I also thank the people who have filled the audience, and I hope that at the end of the talk, they will not feel that it was a waste of time. Let's see how it goes. The title of the talk, as you see on this screen, is Particles and Antiparticles. You know there are particles in the universe. And actually people get a little bit, it hurts their ego if somebody comes to give a talk on particles. They would almost inevitably say that, okay, we know about particles, we know there are atoms, we know there are electrons in it and protons and neutrons, etc., etc. We know. So a talk about particles and antiparticles is bound to be a talk on antiparticles. That is what I am going to discuss in this talk, what antiparticles are, what prompted, what necessitated their existence. As was already said in the introduction, that they were predicted actually theoretically, not even experimentally. So how did that happen? And so on and so forth. You will see. So this is the outline of the talk, and you really don't have to read the outline. I'm also not going to read it for you, because the different parts, when I come to it, I will just mention the names of those parts. So the only thing that you should know from this slide is that here, you should keep your attention here, which will tell you how much talk is left now. Or if you fall asleep inside the talk, just before you fall asleep, you see what was the number of the slide here. And after you wake up, you will see what is the number of the slide. So you will know how much proportionately you have missed or gained in terms of sleep. Okay. So the first topic in this outline is Dirac equation and antiparticles. Dirac was one of the topmost level theoretical physicists of the 20th century. So much so that another top theoretical physicist, much younger than Dirac, Abdus Salam, when he was once asked, who do you consider to be the best theoretical physicist of the 20th century? And he said, it's Dirac. And the person who was asking the question was very surprised. He said, you didn't say Einstein. He said, no, I consider Dirac to be above Einstein. He explained his reasons, which I am not going to. Okay, maybe I should go to. He said that Einstein actually had his mathematics already ready when he did his work. Dirac didn't even have the mathematics. He had to create the mathematics and then do the physics from it. That's why I placed Dirac above Einstein. So this is a very short introduction to Dirac. And now let's see what is his equation and how does it relate to antiparticles. So this is section 1, chapter 1. What did Dirac want to do? There is the classical physics which developed, let's say, until the end of 19th century. And some of the big names of classical physics are Newton. There is Newton's laws of motion, as you have probably already encountered in school, or if you haven't, you will encounter soon. And then also, Newton had the law of gravity. And the other big peak of classical physics is Maxwell's theory, which was the laws of electromagnetism, that is, of electricity and magnetism together. Maxwell showed in a way that those two cannot be discussed in isolation with each other. They are intricately related to each other, and that's why we don't talk about electricity and magnetism separately since Maxwell. We talk about electromagnetism. So these were the big achievements. Of course, there are many other achievements which I cannot really list here. That will take the whole day. But these were the big peaks of classical physics. Now, when 20th century arrived, in the first few decades of 20th century, classical physics a la Newton, Maxwell, received two big blows. The first one came in 1905 through Einstein's special theory of relativity, where Einstein basically showed that Newtonian physics does not work if the speed is for some reason given a very strange word in science, velocity. But velocities are very high, then Newtonian physics does not work. So that was one extreme where Newtonian physics failed. The other extreme came through the physics of very small objects. For very small objects, it was also seen that Newtonian and Maxwellian physics does not work. So for that, one needed some new laws, and those new laws are combinedly called quantum mechanics. So this was the two big blows that I was talking about. Now there was a problem with these two things. The problem is that quantum mechanics was not consistent with special relativity. In other words, as I said, quantum mechanics deals with very small particles. And relativity is different from Newtonian mechanics at very large velocities. So what happens if you have a very small particle with a very large velocity? Then this quantum mechanics doesn't work. So this is what Dirac wanted, to construct a quantum theory which will be consistent with special relativity. And in 1928, he wrote a paper called The Quantum Theory of the Electron. So as you see, he was primarily concerned with the electron, but actually the way he developed the theory applies to many other particles. But we'll get to that later. Okay. Now, in the next two slides, there will be a little bit of mathematics. If you are allergic to mathematics, this is the time for a nap. And tell the person next to you or in front of you or behind you to wake you up after the two slides are over. Then there will be no mathematics again. So, let us consider the simplest kind of particle. A particle which is not under the influence of anything else. That's called a free particle. Okay? So for a free particle, the energy of the particle is just kinetic energy. And kinetic energy is half m times the velocity square. If you think in terms of momentum, which is mass times velocity, its momentum is p and the kinetic energy is p square over 2m. M is the mass. In order to go to quantum mechanics, it's better that we don't talk in terms of E, which is the energy, but we talk of something else, which I called H, which is normally called H. The name is Hamiltonian, but you don't have to remember the name. But this is something, I mean, in quantum mechanics, you don't put in the energy. The energy comes out as a solution of your equation. So what you put in is the Hamiltonian, and the allowed values of the Hamiltonian which comes out through your equations will be the energy values. Okay? This is the relation between the two. Now, so in quantum mechanics, you will start by writing this equation as the Hamiltonian is equal to p square over 2m. Now, this is for a non-relativistic particle. This is what Newton would write. Dirac will have to do it consistent with relativity. And for relativity, the connection between h and the momentum p is different. It is this what I have written here. The h square is c square p square plus m square c to the power 4. This c is the speed of light in vacuum. This always appears in everything dealing with relativity. In fact, when I said previously that at high speeds means speeds comparable to speed of light. So the p square is nothing but the sum of the components square, px square, pi square, pz square. Now this square thing had a problem. The problem is, if you put it in your equation and try to find solutions for your energy, for every positive energy, you will also get a negative energy because they will square to the same thing, right? And positive energies can be anything, all the way up to infinity. So if the negative energies are also all the way up to minus infinity, then that is a problem. You cannot have things whose lower value of energy doesn't exist, because everything sort of settles down at the lowest value of energy. Okay, I mean, if you put a cricket ball on a rough terrain, where will it settle? Where it will have the lowest energy, right? But if you do not have a lowest energy, then it cannot settle ever. It will be forever unstable. Okay? So Dirac thought that this h square is the problem. Oops, sorry, yeah. So Dirac thought this h square is the problem. One should not try to write an equation with h square. One should still try to write an equation with h, but put something else on the right hand side. Now what will you put? So Dirac said that, okay, I will try h which is linear in the momenta. Some alpha x, we don't know what it is, alpha y and alpha z and beta. He introduced these things. So you see, there is no square of the momentum and no square of the mass also. So Dirac thought that this should work. Now how will it work? Well, first of all, you cannot defy Einstein. So if you square it, you should still get that equation which we wrote before here. So think about squaring it. Okay, you will get a term which is c square alpha x square px square. But here you have just c square px square, no alpha x square. That means what? Alpha x square has to be equal to 1. Similarly, alpha y square, alpha z square, and even beta square will have to be equal to 1. But that's not all. When you square this thing, there will also be a cross term, right? A plus b whole square is a square plus b square, but there is also another term, 2ab. So there will be terms like that also. So what are those terms? Okay, first of all, we don't know what is this alpha x and alpha y and alpha z also. So let us not assume anything about them. So if you do the multiplication of this h with another factor of h, you see you will get a term which is like px py, px from here and py from the other factor, right? And that will have a alpha x and alpha y. But then there will be another term where you will have the py from here and the px from the other factor. And that will have the alpha y and alpha x. So the sum of those two has to be equal to 0. Or in other words, alpha x, alpha y has to be equal to minus of alpha y, alpha x. This is not how numbers are multiplied. When numbers are multiplied, a times b is same as b times a. So what does that tell you? Or what did it tell Dirac? It told Dirac that these alphas are not numbers. These must be some other kinds of mathematical objects which do not follow the usual rule of multiplication of numbers, namely that the multiplication doesn't depend on the order. Now, because these are more complicated mathematical objects, the solutions also are more complicated. This is the end of the mathematical part of the talk. So I said the solutions are more complicated. The solutions of what? Okay, I have said this before, but let me say it again, that in quantum mechanics, there is a certain equation, which I am not showing you, and you put your Hamiltonian, the h, in terms of momentum and other relevant quantities, and then you solve the possible energies and of the system and everything else. So this is the equation that Dirac was trying to solve with his h. And this equation is now known as Dirac's equation, So Dirac was trying to solve this equation. And because these alphas and betas are complicated things, as I have said, Dirac found that with a given value of momentum, he is obtaining 4 different kinds of solutions. Now, this is strange. If you think of a Newtonian particle, if you give the momentum, you know the energy, p square over 2m. And so you know that the particle is traveling with this much of energy. But here this is not true. If you tell the momentum, there are still 4 different kinds of solutions. So, 4, that's a big enough number to feel uncomfortable about. Why are there 4 solutions? What do they mean? Fortunately, half of the answer was already known. In 1922, these 2 scientists, Stern and Gerlach, made an experiment, and in order to explain the experiment, Uhlenbeck and Gauss-Schmidt, they proposed that the electrons have 2 spin states. Now, what is spin? I mean, now watching IPL, you know very much about spin, you hear about it every day. So it's something going round around its own axis, right? This is not exactly, it was originally thought to be something like that, but now we know that it's not something like that. However, it is something to do with rotation. Some rotational property which is inherent in a particle. Just like the mass is inherent of a particle, the charge, electric charge is inherent of a particle, spin is something which is inherent. Okay? I mean, by inherent, I mean it's not coming from anything outside, anybody's influence outside. It's something that the particle has, particle possesses. So, Uhlenbeck and Gauss-Schmidt said that electrons should have 2 spin states. And Dirac found that among the 4 solutions that he obtained, 2 of them are really describing the 2 spin states of the electron. And this was a nice thing, because until then, nobody knew why these 2 spin states are coming. Now Dirac showed that they are coming from a fundamental equation. The fundamental equation of quantum mechanics is already telling you that there should be 2 spin states. Good. Half good. What is the other 2? There are still 2 more which need to be explained. Okay. And now to understand this other 2, what Dirac said is, okay, forget about free particle. Now let us say that a particle is moving through the influence of some electromagnetic forces. Now try to solve Dirac equation. Now we will have a different Hamiltonian, different H, which will contain also the influence of the electromagnetic forces on the particle. And now we tried to solve the equation. Still 4 solutions, of course. And the 2 solutions are already known. There are the 2 spin states of the electron. But Dirac found that the other 2 behave in an opposite way in the influence of the electric field. Okay? Opposite way means if some electric field is attracting an electron, it is repelling this other thing, and so on and so forth. Now, this means that this particle has an opposite charge. Of course, the same mass, because they are still coming from the Dirac equation. Remember, there was an m in it, which was the mass. So, the mass is the same, but the charge is opposite. And there was some confusion about it at the beginning. I am not getting into that, because no such particle was known. But finally, everybody said that, okay, this must be another particle which has to be there. Otherwise, Dirac equation doesn't mean anything. For the electron, this antiparticle was named positron. And these other two solutions, remember we had already explained 2 of the 4 solutions. So, the remaining 2 are the 2 spin states of the positron. So, there are 4 solutions, 2 spin states of the electron, 2 spin states of the positron. This is what the 4 solutions are for the same momentum. Okay. Now, this is the theory. As you know, physicists should not take anything for granted until you experimentally observe something. So, people tried to find the positron. So, what was the problem? The problem was this positron, which has the opposite charge. If it meets an electron, as was described to you in a light way in the introduction, they will just annihilate. They will just give energy. There will be no electron left, no positron left, just some energy. And there are electrons all around. The electrons in me, electrons in you, electron in the chair, electron in this podium, and also electron in the air. So, anywhere you use positron, it is bound to meet an electron in a little while and then become energy. It will be lost. So, the trick is you have to detect it almost as soon as it is created. Before it meets the electron, you have to detect it. Okay? So, the question is how to create them and then how to observe them so fast. The creation did not seem to be very much of a problem, because there are many different kinds of particles which are created in the outer space and they land on Earth, they hit the atmosphere and they create showers of many other particles. And in that shower, there are many kinds of things, and one would expect that positron would also be there. Why not? So, these kind of showers are called cosmic rays, and people started to work on cosmic rays. So, that is the creation part. But how to observe? Well, you observe them by some kind of a photographic thing. It is not exactly camera photograph or mobile photograph, but at that time people used to observe them in things called cloud chambers. I am not going in detail of what a cloud chamber is, but it was just some cloud, and if a particle passes through, it leaves a track, and you can take a picture of the track. That is all we need to know for the moment. So, in 1933, Carl Anderson saw this track, and this is history. This is the positron. This is the track. How did he know? that this is the track of positron. Okay, you see the track is not straight. It sort of goes like a circle. Because the cloud chamber also has a magnetic field on it, and things go in circles, charged particles go in circles when they are in magnetic field, or spirals to be more precise, in a magnetic field. And from the radius of this circle, you can find the ratio of the charge to the mass of the particle. So he did that and found that this ratio is exactly the same as that of the electron. But then why is it not an electron? Okay, as I said, the charge is opposite, right? So if the electron is bent clockwise in this magnetic field, the positron would bend anticlockwise. Okay? But then you ask, how do I know? How do I know whether it went clockwise or anticlockwise? How do I know that it went like this or it went like this? One is clockwise, one is anticlockwise. And this is the beautiful, beautiful thing that Anderson did. You see this black thing. He put a lead plate in the middle of the cloud chamber. So when the particle came and it went through the lead plate, it lost some energy because it had to penetrate the lead plate. So because of that, you see that this part is more curved than this part because it has less energy. Okay? So by that he knew that this has to be a positron, not an electron. Beautiful experiment. So Dirac was talking about electron, right? Electron and positron, the antiparticle. So does that mean that the electron has an antiparticle positron and that's it? The story ends there? Let's see. Actually, there is a more general argument for the antiparticles, which has nothing to do with Dirac equations. Now, you see, when you do Newtonian mechanics, what is a typical question that you ask? Okay, you throw a pebble and you ask what is the path of the pebble, right? So you ask what is the position of the pebble at different points of time. So you see that the very nature of the question tells you that you are talking of position and time in a different way. As if time is something basic and the position depends on the time, right? This is something that is not allowed in relativistic theory. In relativistic theory, space and time, position and time are they are not the same thing, but they are sort of on the same footing, on the same pedestal. One cannot be a very different kind of creature than the other. So you cannot ask this sort of question, that what is the position of this particle at a certain time. This is not allowed in a relativistic theory. So what do you have to do? Okay. In a relativistic theory, therefore, you have to deal with objects so that you can ask what is this object at this position at this time. So you take both position and time as your fundamental things and you ask questions about things which depend on space and time. Okay? These are called fields, by the way. This is a terminology which is very funny because it means very different things in mathematics and in physics. Okay. But this is the physics definition of fields, something which depends on position and time. What kind of things depend on position and time? Okay. Suppose I ask you, what is the temperature of this room? You will say where, when. So this is something which depends on position and time. The temperature field, temperature is a field. I mean, even if it is the same in everywhere in this room, which it's not, but outside the room it's different. And 3 hours later, when the air conditioner will be turned off, this will be different in this room also. So you have to know where it is and when it is we are talking about. So this is the temperature field. There is also things like electric field. For example, how will a charged particle behave if I leave it here? Depends on how much the electric field is. And that also can depend on the position and the time. These are called classical fields. In quantum fields, so classical fields actually tell us about the state of the system. But quantum fields do not tell us about the state of the system. They tell us about how we can change the state of the system. And how do we change the state of a system? Well, either by annihilating particles from the system or by creating particles into the system. Quantum physics knows particles. So either it will annihilate, so you give it a system, either it will annihilate or it will create. This is the way it can change the system. So you see that this is a general feature of any quantum field. Quantum field should have an annihilation part and a creation part. But see, there is a relation between the annihilation part and the creation part. What is the relation? Okay, suppose, just as an example, suppose the quantum field reduces the charge of a system by 1, whatever unit. You don't have to worry about. In some unit, it reduces the charge of a system by 1. Now, how can it do it? It can do it in 2 ways. It can, since it reduces by 1, it can be done by annihilating a particle of charge 1, or it can be done by creating a particle of charge -1. Okay? So you see the two parts have different charge. The annihilation part and the creation part. And these charges must have to be exactly opposite. So two opposite charge particles are necessary for this quantum field theory to work. One is the antiparticle of the other. So the positron was the antiparticle of the electron, or you can also say the electron was the antiparticle of the positron. So if you look at it this way, see, we have never used Dirac equation in giving this argument. So that means that each particle should have its antiparticle, unless, you can see what is unless. Unless the particle's charge is 0, because then this should be 0 and this should be 0. There should not be any difference. So if the particle has 0 charge, then it can be the antiparticle of itself. No problem with that. Photon, the particle of light and electromagnetic energy in general, is a particle like that. It has absolutely no charge. So, the photon is its own antiparticle. The electron is not, because the electron has electric charge. Okay. So, now topic number 4. How about proton or neutron? Do they have antiparticles? The proton has a charge, so it should have antiparticle according to the argument that we have given. For the neutron, it's not so clear, but we'll come back to that. Now, they are difficult to observe. Why? Okay, first of all, as I have already said, that the antiparticle must be observed as soon as it is produced. Otherwise, it will meet a particle and that's the end. For positrons, it was easy to produce in cosmic rays. But protons are much heavier than the electrons, so the antiprotons are much heavier than the positron. Okay? So, that is much more difficult to find in the cosmic rays. So, you have to just look for the cosmic rays and keep looking. They are not coming, and you get frustrated. That's not the way to do experiment. Okay? Fortunately, by the 1950s, the scientists are not, the scientists are no more dependent on cosmic rays. They have built these accelerator machines where you can accelerate particles at very high energy and then make them collide. So, exactly what was happening in cosmic rays, remember, things were coming from outer space, hitting the atmosphere, that is the collision, and then they were creating some particles, right? So, now they can do it in their lab by accelerating the particles. And after this state of experiments started, this kind of experiment started, a team led by Segre and Chamberlain found the antiproton in 1955. That is still 2 or 3 years before the BITM was established. Okay. And I have a quiz. Why do I emphasize this 1955? I will not give the answer. Okay. Antineutron was discovered the next year in 1956 by a team led by Cork. So, the neutron also had an antiparticle. Okay, let us not talk about these protons, neutrons and every other particle. Let us just talk about just the elementary particles. Because once we know the elementary particles, everything else is just made up of them, so we will know about them. So, elementary particles, now as we know them, there are different kinds. The one big kind are called fermions. These obey some law which was found by Enrico Fermi and Paul Dirac, the Dirac whom we have seen before. So, why isn't it called by the name Dirac? Because Dirac was so much afraid that it will be called by his name that he suddenly announced that, oh, this thing should be called fermion. Okay? He was a very reluctant kind of person, introvert kind of person, didn't like publicity at all, didn't even like very much talking. Okay. So, he said, okay, these are fermions. So, the name stuck. And among the fermions, there are some particles which are called leptons. For example, the electron is a lepton. it has a charge -1 in some unit. Let's take the unit to be the proton charge. So the electron charge is -1. Does it have an antiparticle? Yes, we have already talked about it. Like the electron, there are some other particles heavier than the electron, but in many ways they are very similar to the electron. They are called the muon and the tau. They also have the same charge as the electron, and of course they also have the antiparticles. But the electron has a partner, and that's called the electron neutrino. That has no charge. And the muon and the tau also have their partner neutrinos, the mu neutrino and the tau neutrino. So the charge being 0, you will ask, do they have their antiparticles? Okay, we'll come back to it. First, let's see what else. We are talking about the leptons, but then there are also these particles called quarks. And there are 6 quarks, just like there are 6 leptons. There are 6 quarks, and the charges of them are either 2/3 of the charge of the proton, as I said, because I have taken the proton charge to be 1. The charge is either 2/3 or -1/3. So because they have non-zero charge, they all have their antiparticles. And the protons and neutrons, for example, are actually made up of them. The proton is a combined state of 2 ups and 1 down. Now calculate the charge in your head. 2 ups, that's 2 times 2/3. And 1 down, that's -1/3. So that's 1. That's the charge of the proton. For neutron, it's 1 up and 2 down. So 2/3 and then minus 2 times 1/3, that's 0. That's the neutron charge. So there are these fermions, and as we see, almost all of them have their own antiparticles. So, by the way, the antiprotons would have the anti-up and the anti-downs. And the antineutrons will also have the anti-up and anti-down. Okay? Okay. Now, apart from fermions, Dirac gave another name to another class of particles. And he said, oh, by the way, all of these fermions have spin half. That's just another way of saying that they have 2 spin states, as I was saying before. 2 spin states. Apart from fermions, there are other particles, which also Dirac named. And the name is bosons. And the bosons include the photon. And here the spin is, as you see, the fermions had spin half in some unit, of course. And here the spin is integer, 1, 0, 2, etc., not half integers. So photons have charge 0, only one photon. I mean, photon is just one kind of particle, and it's the antiparticle of itself. Then there are other particles like the photon, because there are other interactions among particles, not just electromagnetic interactions. There is gravitational interactions, we know, and for that the particle which does the same thing that photon does is called the graviton. This has not been discovered yet, that's why I kept it at the bottom, but it should also be the antiparticle of itself. Then there are other kinds of interactions also, and for them the particles are W's and Z's, which are carriers of weak interactions, and the gluons, which are carriers of strong interactions. There are 8 gluons, and these 8 gluons form a set where everybody's antiparticle is within the set. Okay? And the W, there are 2. One is charge +1 and one is charge -1. they are the antiparticles of each other. So one is called W plus and one is called W minus. W minus is the antiparticle of W plus and vice versa. The Z is the antiparticle of itself. So you see, this is the whole picture. But we haven't talked about neutrinos, right? Now, neutrinos do not have electric charge, that we have already said. So, can they be antiparticles of themselves? Okay, the point is it's not just electric charge which will have to be zero. If a particle has to be antiparticle of itself, it cannot have any kind of charge. Any kind of charge means charge is some number which you count. So, what happened? Okay. Okay. Now, remember I was talking about leptons. So, from all the experiments that we have done, it seems that the number of leptons do not change in anything, in any process. That is, if we give the neutrinos a lepton number equal to 1 and antineutrinos a lepton number equal to -1, then the number, total number does not change. So, the neutrinos do not have electric charge, agreed, but they have this lepton charge, lepton number it is called. And if they have lepton number, then they cannot be antiparticle of themselves. They can be just like the electron. Okay? But who knows whether lepton number is conserved? Maybe we just haven't seen anything which violates lepton number. So, suppose we see that there is some process where this assignment of lepton number does not hold. We will have to conclude that, okay, we should not talk about lepton number at all because it's no good. Okay? And in that case, the neutrinos can be their own particles, own antiparticles. So, if the neutrinos have really no kind of charge at all, then they can be antiparticles of themselves. This is an unsettled issue. No one has seen anything that where lepton number is violated, but that doesn't guarantee that no one will see anything. No one will not see anything. Okay? So, this is an unsettled issue. Now, that brings us to the last topic. Where are the antiparticles? Okay, we are just creating them and within a very small amount of time we are trying to detect them. But are there antiparticles just sitting somewhere around that we just don't see them? Now, in the universe, there is no big accumulation of antiparticles. To the extent that we have seen the universe, even the farthest galaxies and so on, there is no signature of any antiparticle being present. Because if the antiparticles were present, they would annihilate with the particle. I mean, if they are present originally, let us say, they would have annihilated by now with the particles, and only the particles remain and some energy remains, right? So, we do not have any big area in the universe where there are only antiparticles or antimatter. Can we have them in the laboratory? Well, as I said, in the laboratory, the main problem is that your laboratory is made with matter. And so as soon as you create them, the antimatter will annihilate, unless you can keep it apart from your matter. So for example, if you keep if you create an antimatter and can keep it suspending in a big jar, in the middle of the jar, so that it cannot touch the sides of the jar, then okay, you can have it. And scientists have succeeded in keeping them for several minutes, or maybe even a little more than that. I'm not sure exactly about the numbers. To the extent that they can actually study the properties of antiparticles. Okay? But this is still a subject in its infancy. And how much we will be able to achieve in the future, how much we will be able to know the antiparticles of the future, depends on these preservation techniques of the antiparticles, which are becoming better and better, people working on it, and maybe someday some of the students present here will also be working on it. And then you will remember that you had heard a talk on antimatter at BITM on the 2nd of May in 2026. And that talk is ending now.
Wow, I think it's safe to say that we are all going to look at the empty space around us a little bit different now. Thank you for that incredible journey, sir. Can we take a few questions from the audience? Yes, please raise your hands if you have any queries for the speaker.
Sir, why is it that we always see particles with charges of 1? Why not 2? Why not -2? Why not charges more than 1?
No. There are particles with charges more than 1. I was just talking about proton.
Only about protons, but in the chart that you showed, there weren't any. That's why I asked the question.
Don't mumble, say it loud.
There weren't any in the chart that you showed. Like, you showed a table, right?
No,
Yeah.
I haven't shown the charges of everything that we know about.
All right, sir.
Good afternoon, sir.
Okay, is it already afternoon?
Yeah,
Okay.
it is.
Okay.
I don't know if this question sounds very stupid, but you said that if a particle has no non-zero charge, it can become its own antiparticle. And you just said if two particles, that is a particle and an antiparticle, meet, they'll annihilate each other. So are those particles with no non-zero charge actually supposed to exist?
Photon is there. Photon. Oh, you are wondering whether if a photon meets another photon, it
Yeah, I mean, isn't that supposed to be how it goes? You just said that a particle and antiparticle meet, they annihilate each other.
Yeah.
But if a particle is its own antiparticle, is it supposed to exist in the universe? Wouldn't it
Yeah,
kind
because
of
it will
contradict?
annihilate into photons.
Yeah, it will.
It will annihilate into photons. So photons will not annihilate, into photons.
Can you just say that again?
When let's say an electron meets an positron, they annihilate and create photons. A photon creating another photon, even it creates some more photons. That's not called annihilation. Okay?
All right. Thank you, sir.
Good afternoon, sir. I had a question. If it requires magnetic levitation to store antiparticles, why is it that we can only store them for a few minutes?
To be frank, these details of the experiments I don't know very well. I'm not an experimentalist and I don't know very well, but my guess would be that you cannot keep them absolutely at rest. Okay? Maybe you can stop them and to the extent that the velocity is very small, so they cannot move to the jar, move to the sides of the jar quickly, and so on. But still it moves, and after a while it meets. Okay? That's my guess.
Good afternoon, sir. Sir, I had the doubt, if neutrons do not have any charge, then how could anti-neutrons exist?
Okay. Neutrons do not have electric charge. They have another kind of charge. Just like for neutrinos, I was talking about the lepton charge.
Yes, sir.
They have something called the baryon charge. Okay?
Okay.
So that they have something which distinguishes from the
Thank you, sir.
anti-neutron.
Why is it that there is like such an enormous amount of matter in the universe, but there is so little antimatter? Like during the Big Bang, did like only matter form? And how is it that sometimes from cosmic rays we get antimatter? Shouldn't it have been annihilated long ago? Like, why is it that there is so much more matter rather than antimatter?
There is not very much matter in the universe. Okay? I mean, this is from our egoistic point of view that we think there is a lot of matter. If you think of how much matter there is compared to how much photon there is, the ratio is 1 part in 10 to the power 10 or something. Okay? So there is not very much matter. And what scientists think is that in the beginning of the universe, that is close to the Big Bang. Okay. So close to the Big Bang, there is a little excess of matter over antimatter. And even if there were antimatter, they have annihilated, and now we see just the matter. Okay. The question is, why was there a excess of matter over antimatter? Sit down. And you can have two kinds of answer. You can say that there are more matter because there were more matter created. I mean, it's just initially more matter was created. If you start answering this way, then there is no science at the end. If you ask, why this happens, that happens. If you say, why the moon have phases? Moon has phases because, moon likes to have phases. Okay. Why the sun rises in the east? Because the sun actually comes from the east. So the better way of trying to understand this question, the answer to the question, is to say that, okay, maybe they started the same number, but somehow there were some processes which created an excess of one kind over the other, and that excess kind we call matter, and the subdominant kind we call antimatter. Okay. There are theories about how this can be done. And there are conditions that need to be satisfied in order for this to happen. But these theories are not, how should I say, very, very, very robust theories. I mean, these are sort of, the scientists also debate about these theories and so on and so forth. So there is no clear answer yet. Okay. So that's as much as is known. Somehow the asymmetry was created by some process.
Yeah, so my question was, we know a proton has a much heavier mass than an electron, and hence in an atom the electron revolves around the proton. Does a positron and an antiproton also share similar properties?
The mass of the particle and the antiparticle is always the same.
Yeah.
So yes, the positron has the same mass as the electron, and the antiproton has the same mass as the proton. So if there is an positron going around an antiproton, that will be called an anti-hydrogen.
Anti-hydrogen.
Yeah, because proton and electron makes a hydrogen, right?
Yeah.
So just one proton and one electron makes a hydrogen.
Yeah.
So if you have an antiproton and there is a positron, that will be an anti-hydrogen.
Also, does anything happen when, say, an antiproton collides with a positron or a particle with non-zero charge, like a photon? It will collide when we are keeping it in the magnetic leviation to see them. It will collide
Can you
with
start from the beginning? I got lost.
When we are keeping antiparticle in a magnetic leviation, to see them, a photon will collide with them. So does that collision cause any effect or something? That's my question. What happens when two antiparticles collide with each other?
Two antiparticles collide with each other.
Yes.
That we haven't seen yet, but there are theories about what will happen. But nobody has seen an antiparticle colliding with another antiparticle. We haven't gone into antiparticle research to that extent yet.
Or an antiparticle collides with a particle of non-zero charge. Zero charge.
That can happen.
That can happen. Okay.
I mean, you are thinking of
Last
an
two
antiproton colliding with a photon.
No more question. Last two question.
Sir, প্রথমে আমার প্রণাম নেবেন. I have a small question that when I go through the part called quark confinement, so there they have said that the quarks particle, they are interacting with each other with a gluon.
May I stop you here? Could you ask me this question outside the thing, because I don't want to sort of go outside what I have talked about.
Okay, sir.
Okay?
Okay, sir.
Please ask outside.
Last one.
Sir, you have told that particle and antiparticle annihilation gives off energy, but it violates the second law of thermodynamics, which states that no energy can be created or destroyed. So, how is it accepted?
No, the particles have energies. Come on.
Yes, sir.
Just because they are particles, you don't think that they don't have energy. They can have kinetic energy, they have the mass energy, and so on. So particles have energy, and that energy is converted from being in the particle form to, let's say, photons.
And sir, can this energy be used for something, this energy obtained from particle and antiparticle annihilation?
You mean technology?
Yes, sir, in anything. Can it be used?
Well, there is some technological use which already the director talked to you about, the PET. Okay? So, yeah, there is some use certainly. Yeah. Okay, but there is one thing I want to talk about. The sanctity of a theory is not determined by whether it is used for humankind for something of their own, to make something simpler. Okay? In other words, technology can happen, but even if technology does not happen, the scientific theory is there. I mean, there is a famous line in one of Sherlock Holmes stories that has anybody benefited from the knowledge that the earth goes around the sun? I mean, this did nothing to our life, right? But it's still knowledge. So it doesn't have to be that it will be used for something to the benefit of mankind, but if it can happen also.
Thank you, sir.
Okay, thank you, sir.
Thank you, sir. And as we bring this brilliant morning to a close, it is my privilege to propose the vote of thanks on behalf of BITM and the National Council of Science Museums. First and foremost, our deepest gratitude goes to our speaker, Professor Palash Baran Pal. Can we have a big, high energy applause for him? So thank you for making the elusive and complex world of antimatter so incredibly accessible to us all. Your ability to translate high-level quantum mechanics into a story that captivates a room full of young minds is a true gift. Thank you for spending your morning with us. I'd also like to extend our thanks to the National Council of Science Museums, Ministry of Culture, Government of India for their unwavering support of BITM's mission to take science out of the textbook and into the real world. To the principal, teachers, and escorts who have accompanied the students today, thank you. You are the vital catalysts in our lives, lowering our activation energy required to turn curiosity into actual knowledge. A special thank you to members of the press and media present here today. In physics, we know that information must be transmitted to be useful. Thank you for acting as our photons, carrying the light of scientific awareness from this auditorium across the city. To the officers, staff members, and all associated from the BITM family, organizing an event of this magnitude requires massive transfer of kinetic energy. You are the strong nuclear forces that hold the institution together. Thank you for your tireless efforts behind the scenes work to ensure the 68th Foundation Day of BITM goes entirely frictionless. And finally, our biggest thank you to our students. Your sharp questions, your curiosity, and your brilliant energy are the real reason BITM has thrived for exactly 68 years today. You are the future of science. Thank you everyone for making the Foundation Day lecture a massive success.